The topic we are talking today is RF simulation and analysis. And I'm Jifan, I'm from Singularity Engineering. We are going to start off introducing our company. So we are Singularity Engineering. We are Bay Area based companies, and we are also ANSYS certified channel partner. We support the full portfolio of ANSYS simulation tools. We support structural mechanics, fluid dynamics, and electromagnetic simulations. So the agenda today is going to talk about how can simulation help, and next we'll do some simulation demonstration, which includes impedance matching, radiation pattern in free space, radiation pattern inside enclosure, and I will show you the power dissipation. And at the end, we will talk about a scenario setup, which is a car radar scenario. So how can simulation help? As many people know, like antenna is typically usually designed in ideal condition, and once we put this design antenna into real world, there will be some malfunctioning, and the result you are getting in the real world is not as expected in when you design ideal conditions. And we also know ray paths are complicated, and it's very hard to see how the rays goes and back. And also, antenna design, both far field and near field effects are content. That means in simulation, you can see your near field and far field effects, but in real world, it's quite hard to identify what is the near field effect and what is the far field effect. And the last thing is, last but not least, antenna performance prediction is what we usually are most interested in. So when we do individual antenna design, so we have the performance of this design and what happens if we put it inside a radome, and how does the radome affect the performance, and what happens if we put this antenna in your radome and then inside application of the structure. This might impact the entire design. So next we'll go to a demonstration. First, we go to electronic desktop. Let's see. So if we go to file, we have imports. So we support like AutoCAD, ODB++, Cadence Aligo, and IPC, AWR, etc. So the file we use today is ODB++. Usually for the answer, electronic desktop ODB++, you are supposed to import like one typical file. What happens if you have the ODB++ in a folder type? So in a top folder, you usually use SI wave. So if you go to SI wave, here you can go to import ODB++ design, and you browse to where your design. So the ODB++ is in a folder. So if we select this folder, we import it. And from here, you can see your design. So in this, once you import the design, you always want to check your layer stack. So you can go here, layer stack, and you can see you have all 4 layers, but something is missing. What is missing? We are missing dielectric between these layers. So this can cause by when you export this file from another software, or when you import, so the file is not, so this design is not completely exported or it's not, and or when you import it to SI wave, it's not completely imported. So so when you export the design, usually you need to look carefully about what you are exporting, and when you import it, always double check. So because this file is an open source, so I'm not sure. So it's supposed to the problem is whether come from the other side or my side, but I will import the dielectric layers manually. So here I have a design which already have the dielectric layer. If I go to here, let's file. So in this design, if you check the layer stack out, you can see there's dielectric layer in between. So next, we are going to export this into HFSS for 3D simulation. So before you import, you always want to select everything that you want to export to HFSS, and you can always preview first and then export. So I will just go ahead and export. Yes. And SI Wave is another tool that ANSYS developed, and this tool is mainly used for signal integrity. We have another video on signal integrity. If you are interested, you can always look it up. So now we have the file exported here. Okay, anyways, so let's look at this file. And so from here, we can see what we have is this PCB file. And if we look at the model, here we have all the solids. So this is the error box, which we can delete. We are going to create another one. And we have all the copper layers and traces. We have the dielectric. And here we have all these ports are generated automatically when you are exporting the files. But there are some useless here, so I'm just going to delete all of them. Now we are seeing we have this trace, and here we are missing an antenna. So the antenna they use is from Johansson technology, and where we can simply, so we have Johansson technology from our library, so we can just simply take it out from the component library. If we go to component library, Johansson GPS antenna, so this is the one, and we just simply drag and drop, and it will be there. And we just need to move it to the right location. Hide the dielectric. So if I move this, okay. So we can see you want to make sure the here is touching the metal, so it will run the simulation correctly. Now we need to set out the port to run the simulation. So here, this is the trace that we are going to use for this simulation. So we are going to create a port here. But first, before I create a port, I want to make a ground. So I create a coordinate to split this by YZ, okay, the negative side, and here. So I will assign this one as my ground. So I just assign boundary and then perfect electric field. So which means ground, and you can see your boundary here if you click on it. And right now I need to make a port. So if I click here and here, So when you see the rectangle, you know they are touching perfectly, and you want to making sure they are touching each other to make it a good port. So here, we want to change the size, and what we can do is, if we measure edge, we want to measure the edge. So we have the length here. Just copy and create. Just paste it. Apply. So now we have the ports. All right. And we need to assign LAN port here, and reference, which is this one, is your ground, so you put it as reference. Once you assign the port, you can check it in your project manager. You have the excitation and you have this port. This is your reference point. All right, now we have the trace setup. And next is we need to set up an analysis. So for our simulation, the frequency is 1.575 for the GPS antenna. Okay. And we also need to add frequency sweep right here, 4 gigahertz, and I want to do linear step. And okay, so for the sweep type, you can either use interpolating or use fast. So this will make sure your simulation run fast enough. Just click OK. Right now, one thing is missing. So we have all of this, and we are missing an error box. So the size of the error box, we typically use a quarter of lambda. So a quarter of the wavelength. So after my calculation, a quarter of wavelength is around like 50 millimeter. So I will just measure absolute offset. So here create boundary, absolute offset, and then 50 millimeter. So it will give you this error box. And we need to, so because we want to see radiation patterns, so we want to assign this boundary as radiation boundary, so you can get a radiation pattern. And then here you can see that radiation, so you insert far field setup, infinite field, and 3D. I believe this is good. Coordinate system, we typically use where the antenna is located, which is relative CS1. Okay, so now everything is set. You can validate your design. If you see everything is green, just analyze and it will run. So because the complexity of this board, and so it will take a bit longer to run. So I have already have one that is already simulated. Let me go ahead and open that one. And right now, see, so we have the same design, everything is the same. So the simulate, we already have the result. If you want to see the result, just go to result and right click, terminal solution and rectangular plot. Here, you can get your S parameter, Y parameter, Z parameter, VSWR, Z naught, anything you want. And you just need to create like new report. And here you can see your S parameter. If I right click, add marker, I can see at this point is 1.57 gigahertz. But yeah, the return loss is not quite meeting my expectation. So I want to match this to make sure it have a good return loss. And another thing you can look at is also your um, impedance. So when at this point across the origin, that means it's matched to 50 ohms. But yes, so let's match the circuit. So there are many ways to match this circuit. You can so the way we are using here, we are using a circuit. So if we go to project, insert circuit design. So it give you this circuit design, and you simply just drag and drop this into circuit 1. You turn this 3D model into a circuit model here. All right, let's see. So this is your circuit model. And this port is the port we set up in our 3D design. And right now you can only see the input port, but we want to make it clear so you can see like the input and the ground. So if we go here, we just add individual reference point. Okay. So you have your port and ground. And let's add another port in the circuit to it. And for this port, we want to use microwave port. And we need to give it a excitation here because circuit is separated from the 3D model. So you need to reconfigure these things here. So we put it 1 volt for the AC magnitude, and we are at 1.575 gigahertz. Okay. Okay, and you see there's a excitation right here, and you need to give it a ground. All right, another thing we need to do is set our analysis. We just do linear network analysis, and we just add here. I believe the one we did is linear step from 1 to 4 gigahertz by 0.01. And it's okay. So everything is set. Next, we are going to run a simulation. The simulation in circuit usually takes very quick, maybe just 1 or 2 seconds, and if it's finished, if you go to result, standard plot, and the result here should match what you see inside in your so it should match what you see in your 3D model. So here you can see you have the exact same S parameter. And what's the purpose of this? Because so the purpose is we are doing matching, and we are using Smith chart to doing matching. So first, you want to locate your let's say 1.58 point here. So we have 1.58, and then you can see your frequency at the right bottom corner and 1.58. So we want to make a conjugate. So if I make it here, so you can see your conjugate here. Now we can start matching, new match, create a 50 ohm. You can either just enter it here or just click it here. Now let's see. We might need a shunt capacitor and a series capacitor. So for the first one, if you don't know the value, you can just pull it around. So to see where it matches. So we can see we use like 9.57 femtofarad, or we can either use 1.03. So it's just a little bit of difference, not a lot. And you can just export this circuit. So once you export it, okay, and okay. Now here you can see your L matching circuit. And if we go back, so we just like drag and drop. One best thing I love this tool is you always do drag and drop. You don't really need to do anything complicated. And we're going to now analyze. Now we have a better S parameter. If you can see, oh, we have at 1.57 around negative 25 dB return loss. And if we look at S parameter, data marker, yeah, 1.57, very close to the 1 point. Fair enough. And now, so what happened if we put this circuit into our 3D model? So see, right now we don't have anything matching. Now we want to put this L matching circuit into our 3D model. So once you can do is you do the same thing. You just split this into half, and then you just create a few port. And I have it already because timing issue. I already have it created. So let me check it out. If I just go here. Okay, so as you can see, I put two sheets here, and then I just simply by right click and assign boundary, lump RLC, and here you can give your either capacitance value, inductance value, any value you want, and then you basically just assign. If you use like we usually use variables, so it's easier for you to change the value that you want to use. Let's say if I want to put C3, you click OK, so you enter your value here. And if I go back, if you go to the project manager, so go to your boundary, you can see I already have these two capacitors here, right? And everything else is the same. And if you want to see your value and modify it easily, so just go to this HFSS model and then design property. Here, you can see the value. Oh, yeah, so this is the value actually we got from the circuit. So I remember it was 1.03, but I'm using 1.05. Just a minor difference that's not going to change by too much. And I already have the simulation done here. So I just go to result. And if I look at the S parameter, you can see it's at 1.59 gigahertz. So the frequency a little bit off. Why? Because the position you put your capacitor actually matters in PCB design. So no matter where you put it, because I match it from here, so you have to put your capacitors here. But because there's no space, so I put my capacitors here, and that means you have to match your circuits. But why did we do the step like previously? Because we after we use that is easier to tell you the value of the capacitors. And then once we have these values, we can use these values to do optimization and make this circuit match perfectly. So next, the thing we want to do is we need to create two port here. So I have it done in the other circuits. This one. So I already have that done the same, except they are not lump element, except they are not lump element anymore. They are ports. And then one thing I need to do is I put this 3D model into circuit again. So if I go to circuit design, drag and drop. And one thing to mention is why do we want to do optimization in circuit, and why do we want to do all this tuning in circuit? Because it takes much faster than you do in HFSS 3D model. So once we have this circuit, you see, and we want to see all the pins. I want to see all your points. And you can manually move this around. I like to put it this way. Okay, so what you have here is a shunt and series, and what you have there is you have two capacitors. So you just go to component library, drag and drop, and there we go. So you just basically connect them all together. And if you don't show all the pins, if you just connect a capacitor from here and the other side of the capacitor, if you connect it to ground, that means you are connecting this to ground instead of you are connecting between nets and nets. So that will give you an error. So typically we always want to use all the pins. And we give you a port. So for here, you don't need to make it microwave port because it becomes like a circuit. And you don't need excitation as well. You just set up an analysis. There we go. So we have 1 to 4 linear step 0.01. I believe so. Okay. And I want to give them some value. If I put C1, it's like 1.05 picofarad. Okay. And I believe this is C2 is 6.55 picofarad. No, I actually put it here. You just click OK. So if you run the analyze, you can see the same result here. There we go. So now you see the result. We want to tune it right now. So there are many ways to tune this. You can either use parametric. So that's why you want to use variable. So you can use, if you know like what range of this value, you can just enter it here. Let's say I want to put 0.5 to let's say 2 by 0.01. Add it and okay. Oh, I need to add another one. So C2, let's say so I put 5 to 20 by 1. Add it. Okay. Click OK. And you can just go ahead analyze it. Or another way you can do is you can do optimization. So this make your life easier. It's just set up calculation as parameter, all of this. And we want to add one typical frequency. So we choose at 1.58 and add calculation. So here, what's the condition? We want to make sure it's smaller than negative 10 dB, so it gives you a good return loss. So we use a number negative 10. Okay. Okay. Oh, no variable is included. Yeah. So it's so if we go to here, variables. Oh, no variables included. So we go to design property. We want to make sure we include all these values. So there we go. And then we just apply. Okay. If we go back, uh, this is not the one. Optimization here. So we will just make it override. Okay. And same thing, just analyze it. And I'll disable them right now because I have a third way to do it, which is tuning. So tuning, here we have 0. I will put 0.5 to 1.5 here. I will put 5 to 30. So here, and just let it. Yeah. One more thing you want to see is you want to add marker. So you want to make sure you are at 1.575 gigahertz. Okay. So now let's do something fun. If you just slide the bar here, look at this. All your S parameter are changing, and you can give it deeper, so it give it more return loss. So yeah, close enough. Put, let's say 28 here, give you a pretty good gain. I believe it's 1.6 here. If I put 2, yeah, put 1.6, yeah, something like that. Look at this, it gives you a pretty good return loss at 1.575 gigahertz. And I want to save these values. So right now, if I go ahead and save it, I like to do the tuning way because I can see more and I can see how the S parameter change. So it makes, I think it's more fun doing that way. But if you are time consuming, you can if you want to save your time, you can do optimization or anytime. And I will just go ahead. Let's look at the S parameter. So it's exactly the same. And what happened to our Smith chart? Smith chart. New. Hey, we are not at the right frequency. So here C1 we were at 1.6 pico and we were at 28. All right. If you add a marker, you can see pretty close, fair enough. And now we want to put this back into our circuits. So we just go back to our 3D model. We delete all these ports and we give them, we do the same thing. Assign boundary and we give it a lump RLC and capacitors C1, C2, and I already have this. And then after you set it up, just run another simulation. And or else I have this way. I already have this simulated. Take a look. Right now we have this. If we go to project manager, hey, you can see your boundary here. So you have your C1 and C2, and you have your excitation. So everything's set, and let's look at our S parameters. Oh, it's at 1.57 gigahertz with negative 30 dB. So the result is much better. And if we look at our Smith chart, very close. Okay, so what's our next step? I'm going to solder the radiation pattern. So as I mentioned, I have I create this 3D radiation, and then if I go to results, create a far field report radiation pattern, and then again gain total. I want to look at the gain total dB. Oh, supposed to using elevation. Look at this. We have our radiation pattern here. So, and then one, because we have it at two different angles. So let's do a 0-degree applied trace, and you can look at this. And this is your peak peak gain for your radiation pattern is around 0 dB. So it's like 0.02. Yeah, very close. So, and we can see this over our design. If we go here, just rotating it, now you can see your radiation pattern over your design. And you can actually see how it looks like. So now next, we want to look at the 3D polar plot. If we go here, just far field report, 3D polar plot. Same thing, we use dB. Well, and you can see a 3D polar plot. And let's plot it over your designs. Look at this. This is how your 3D polar plot looks like. And here we have our radiation pattern. Looks very nice. And if we go to the radiation, and here we just right click, and we have our antenna parameters. Here you can see your incident power, which is the power you put to the port, and you can look at the accepted power. So this is the power that is accepted by the trace. So it's close to 100%. That means your matching network is pretty good, well done. And then you have the radiation. There's the radiated power. So it's 55% of the accepted power. So only like 5.439 so milliwatts out of 9.97. So where are all the other powers goes? So we want to see where are all the powers go, and we want to also look at. So if I just go to dielectric, dielectric, and then we just right click plot field, others, volume loss density, field calculators. And if we go here, just find the volume loss density, copy to stack, and you find the geometry. So you have all your nets, layer, everything here. You have your radiation box, dielectric, anything you can find. And if we just look at the dielectric, just click it, and then integral. Well, then it will give you a value. So it is 1.97 milliwatts. So that's close to 2 milliwatts. So from here we can tell that there's almost 2 milliwatt of power dissipated to the dielectric. And if we click done, and you can also go to assign material, and you can look at your dielectric FR for epoxy. So yeah, we have our dielectric loss tangent. It's like 0.02 here. So that makes sense. Okay, now we have our antenna matching done, and we have our radiation pattern. So this is your radiation pattern in free space, And what happens if we want to put this inside the car? So now you need to create your any structure, like let's say car model, or you want to make it like a. If this is chip is for your mobile phone, you just need to create a CAD model of your mobile phone and anything. So right now here, you have your car, and first thing you need to do is make sure you give it a right boundary. So because it's shit, you don't know what material it is, so you want to give it a perfect E. Make sure it's because it's copper. So I just make it all ground, and you need to also assign a hybrid region. So another one of the technique we use is SBR plus. So that's shooting and bouncing rays that allows you to calculate all the rays that bounce off the car or shooting the car and in different directions, and this can increase the accuracy of your radiation pattern and increase the accuracy of your simulation. If you just go to boundary, oh no, my bad, it's assign hybrid. So usually just here because I already assigned it, so it's not appear there. If you click there, SBR plus region, and we have the IA region that's not for much larger structure, so like an aircraft, because if you simulate the entire aircraft, that takes forever. So for IE, you just simulate the surface of the aircraft. And now we just need to make this a 3D model. Make this as a 3D component, and then we want to import it into our design. So now we have our design here. We just go ahead, import the car model. If I go to let's see 3D component library, browse, and we just need to go to share. Yeah, ultimate. We have a full car here. You can look at it. Just open it. Go. Now you have your car. So the next step you need to do is move this GPS around. So if I just move, click anywhere of it, and let's say you can move to your back bumper, you can move to your front bumper, move to the top of your car, bottom, anywhere you want. But I typically just put it because it's a GPS. I assume it's a GPS. So I just put it in front of the car as a yeah. If I put it here, and you can do the other way around. You can just move the car around instead of moving this 3D model around. And then after you move it, I don't want to see all of this. Disable them. Anyways, so and then you just need to run another simulation, and then I have that done. So this save our time. Hey, so I have our design here, and you can look at this radiation pattern, and Yeah, so it's completely different than what you see before because you have this car model and you have this certain bouncing rates and you kind of includes everything in your environment. So you have this um, weird shape radiation pattern, and your gain of the radiation pattern is actually changed because you can see this is kind of your main lobe, and you have all the side lobe, uh, and the gain of the main lobe is increased. So if you look at this one, and you can also look at your 3D polar plot. If I just go, hey, it looks like some kind of explosion there. Look at this. And you can also change your scale of this plot field, radiation field. I want to make this look bigger. We'll try scan plot one. I want to look at this. Apply. Hey, I can. Now you can look at your. Alright, so this is the end of the car model, and let's go back to our slides. So conclusion, we showed you how to use parametric and optimization. You just set it up and just make it run. Usually optimization gives you save you the most time because you don't need to do everything hand on. You just do optimization, let it run, and you give you the result that you want. Parametric, you need to know like what's the range of the result that you want, and you can look at the other result within that range. And all of these are done in the circuit, but they can be also done in the 3D model. But in the 3D model, it will take a little bit longer because it needs to simulate the 3D model as a whole instead of inside the circuit. You just look at it as a black box. That circuit is a black box, so that makes it faster. And we have also done the impedance matching. So if we look at this, first we match it from scratch. Now we put inside this lump element at certain position, and then we tune it. And also, so our impedance change, our S parameter change from negative 8.6 dB to negative 30 dB, and we also match it at the right frequency. And here, one thing I didn't show you is if you look at the antenna parameter here, the accepted power is much less than here because the circuit is not quite matched. And yes, so we also look at the power dissipation. We have the lossy material, and we can calculate how much power dissipate in this lossy material. So in this case, you can consider whether you want to change your material property or not. And we also show you the radiation pattern in free space and inside a car. And we can. So last but not least, I'm going to show you the car radar scenario, and I believe this is most people interested in industry. So we all know install antenna performance can impact the overall RF system that you design, and if you mount your antenna onto your realistic platform, that can change the performance as well. So now we have this radar, car radar, and we mount it in at the fascia, and we also have this rough surface scattering environment. There will be reflection of the road. And let's look at our setup. So right now we have this car with the radar antenna on it, and with this car just driving towards our car. And we have this as a per scatter model. So this is not using any technique of ANSYS. And so right now we can just we treat this car as a point, so we don't see any reflection of that, and we're using parametric beams. So that means it's there are no side lobe, and we are using SPR plus. That means we can actually see the certain bouncing rates. So we treating this incoming car as a car instead of a point, and we can see this car is moving at around 30 meter per second, 10 to 30 meter per second, and we can see that here there's something reflected, and it's also silo free, so it's using parametric beam. What happens if we install this onto the fascia? So after we install it on the fascia, we can see a lot of silo, and at the far end here, because in our setup we didn't put anything here, we didn't put anything at that point. So what is reflecting? And what is reflect? So this reflection is actually from the road, because we have the rough surface of the road, and there will be some kind of reflection of the road by the side lobe. So this car is driving at like 10 meter per second, and we can see this thing is moving at 10 meter per second. So this is the reflection from the road. And yes, so if you are, so this will conclude our topic today. And if you are interested in any of this simulation or our scenario setup, you want to see more about it, please contact us. And I'm Zifan, the application of engineer of Singularity Engineering. And you can always feel free to contact me in the email phone number below, or you can just comment under our YouTube channel, and we will get back to you. Thank you.